Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 2 of problem set 6, the Bohr model. Number 6, the energies of photons emitted by one electron atoms and ions fit the equation, where Z is the atomic number, N1 and N2 are positive integers, and N2 is greater than N1. Is the emission associated with the N equals 3 to N equals 1 transition in a one electron ion ever in the visible region? Why or why not? Okay, remember the visible region on the electromagnetic spectrum is between 400 and 700 nanometers. And because we're using wavelength a lot of the time, I find it easier to use the Rydberg equation to solve this problem, not the equation that they give you. I know it's a little deceiving, and really they kind of want you to, but it's just a lot easier if you use this one, because what we're looking for is wavelength, right? To see if it's somewhere in this region. This equation is really only helpful when we're looking for energy, which is kind of obvious, right? We're looking for energy here. But this equation is literally a derivation of the Rydberg equation, this guy right here. They just have slightly different variables. You can kind of see the similarities, but really the Rydberg equation, in my opinion, is going to be a lot easier. So here, let's use the Rydberg equation here. I got 1 over wavelength is equal to RH, and I know that N1 is going to be the smaller n, so I'm going to put 1 squared minus 1 over 3 squared, okay? And this ends up getting me 1.02, okay? Remember that when you multiply these together, you got to invert this so that you can get this into just regular wavelength. Okay, and I get 1.2 times 10 to the negative, or about 1.3 times 10 to the negative 7th meters, which is equal to 103 nanometers. Now, this is outside of that spectrum, right? So I'm not going to see it. This is actually in the UV range, okay? So I'm actually not going to see this. And to be frank, the why or why not, it's just going to be because it's outside the visible region, okay? No, outside. I'll just put outside, okay? That's going to be the answer that you want. All right, number 7. Balmer observed a hydrogen emission line for the transition from N equals 6 to N equals 2, but not for the transition from N equals 7 to N equals 2. Why? Before you do a bunch of math and try to solve, a bunch of equations using these transitions, don't. Because you don't really need to. We're just comparing this and this. And if you notice, this has a lower energy transition than this one, right? We're ending at the same place, but for this one, we're starting at a higher energy level. So that means we're just going to have higher energy. So the transition here must be within the color region, but this one must have a higher energy than the color region, which happens to be ultraviolet, right? If you look at, this is 400 nanometers and this is 700, that means it must fall out into this range, which is UV, right? Ultraviolet. So really, that's all it is. The energy here is outside the color region, outside color or visible region of the electromagnetic spectrum, okay? That's really all there is to it. Not too bad. Number 8, the following diagrams show the emission and absorption spectra in the visible region for hydrogen gas. Label each spectrum label which spectrum corresponds to emission, which to absorption. Okay, emission, when you emit light, the only way that can happen is if an electron that was originally excited by a photon of that same wavelength drops down to a lower energy shell and re-releases that photon. So if this is N equals 2 and N equals 1, the only way that this can emit something is if it first absorbs a photon of that wavelength that exactly matches this energy transition. Remember, photons have energy, right? They're quantized. There has to be a photon with exactly this energy that can get absorbed, and then it just gets re-emitted, and then it goes through that whole process, and then you just get a bunch of photons getting emitted from here. Okay, and that's where we get these lines here. And that's the only way that you can get emission. The rest of the photons do not fit some of the transitions, right? In fact, most of them don't. And so they're all going to be absorbed. We're not going to see them again, okay? So we're hitting light at them. So this is going to be the absorption spectrum, absorption. Okay, and this one's going to be the emission. Because emission is very specific, I have to have very specific photons that can transition between certain levels that produce these wavelengths. And in fact, what we see in any color is actually, if you ever get diffraction glasses, really what they are, all they're doing is separating the colors that you see combined. These colors will actually add up in your retina to a color that you see that isn't actually any one of these. It's just a combination. They just all add together, okay? So anyway, part B says the wavelengths of the 4 lines in the visible region of the electromagnetic spectrum are given. Describe the transition producing the line at 486 nanometers in both spectra. What energy levels are involved? We'll get to that in a second. Whether a photon is being absorbed or emitted. Okay, now we know that a photon has to be emitted right there. Otherwise, we wouldn't see it. There wouldn't be that line right there, okay? So Again, they're gonna like throw this this energy equation at you, but honestly, I would just not use it. Just don't use it. Okay, I would use the Rydberg equation, just so much simpler. So do 1 over wavelength is equal to Rydberg constant times 1 over n1 squared minus 1 over n2 squared. That's it. Okay. Now here, what we actually are going to solve for is this variable, right? And you're looking at me funny probably because there's actually two unknown variables here, but I'll get to that in a second. Okay. So let's solve for it. In that case, I'd have to divide both sides by the Rydberg constant. So I'd get 1 over wavelength times Rydberg's constant is equal to 1 over n1 squared minus 1 over n2 squared. Now, if you do that, in this case, I got what? This wavelength here is going to be 486 times 10 to the negative ninth meters, okay? And then this constant here, I'll just erase it so you can kind of see. This constant is actually, it's on your equation sheet, but it's 1.0974 times 10 to the 7th, and then the units are 1 over meters here, so actually your meters are going to cancel. And so if you do this and you invert, right, you got to invert this, okay, right, -1. Okay, invert it, and then you end up getting 0.1875, okay? Now, you're probably wondering, okay, what the heck do I do with this? Now, a lot of times what they're going to tell you is to guess and check. Plug a bunch of numbers in here until you figure out which ones get you to 0.1875. Honestly, it may end up just being a huge waste of your time, and I'm about to save you a ton of time by using the following trick, okay? Here's the trick. If this value, okay, falls between 0.75 and 1, the ground end shell is going to be n1, n equals 1, which means this n1 right here, this guy right here, that's going to be equal to n equals 1, okay? Or if the difference is between 0.139 and 0.25, the ground end shell is going to be n equals 2, okay? That means the n1 right here is going to be equal to n equals 2. Now, that's going to save you a ton of time, and I'll show you why. So let's say, so I've got this 0.1875, and I'm going to set that equal to 1 over 1, n1 squared, 1 over n2 squared, okay, is equal to 0.1875. Okay, now, I notice that this value falls within that range, right? Okay, so I'm going to assume that n equals 1 here, this right here, is 2 squared. So that means it's 1 over 4. So I'm going to solve for this guy, because now I only have one variable to solve for. So 1 over 4 minus 0.185, whoops, not 1 over 0.185. Okay, 0.1875 is equal to 1 over n2 squared, okay? And that would be 0.25 minus 0.1875. And then I'd have to invert this, okay? And that would give me n2 squared. And then I'd have to square root the guy, okay? Now, if you do that, you actually get 4, okay? What does that mean? That means it went from n equals 4 to n equals 2, okay? And it had to be going from the higher one to the lower one because it's emitting something, right? So it's going from high to low. So yeah, this would be the transition, the n equals 4 to the n equals 2. That would be the answer. Just using this rule, right? I didn't have to plug in a bunch of guess and check, which is what they're going to tell you to do. Trust me, I've TA'd for forever, and that's what they're going to tell you to do. But this trick is so much easier. So let's use it again here. It says, the hydrogen atomic emission spectrum includes the UV line with a wavelength of 92.3 nanometers. Is this line associated with a transition between different excited states or between an excited and the ground state? Okay, ground state just means it's going to be n equals 1. So let's plug it in. 1 over, and then this would be 92.3 times 10 to the negative ninth meters, okay, times the Rydberg constant, 1.0974, times 10 to the 7th, 1 over meters, so my meters are going to cancel, is equal to 1 over n1 squared minus 1 over n2 squared. All right, now if you do that, remember to invert this, okay? I get 1 over n1 squared is equal, or minus 1 over n2 squared is equal to 0.9873, okay? Now, what do you notice about this number? This number falls between 0.75 and 1, so I'm going to assume that this n1 here is going to be n equals 1, okay? So I'm going to plug that in. I'm going to say this is n equals 1. So 1 squared, which is just 1, right? So I'm just going to put 1 right here. And then I'm going to add this over here. And then subtract this guy over here. Let's see. 0.9873. So it becomes 1 minus 0.9873 is equal to 1 over n2 squared. Okay. Now if you subtract 1 minus 0.9873, you get about 0.0127 is equal to 1 over n2 squared. Okay. Invert it. -1. -1. And then I get about 79 is equal to n2 squared, and then square root both sides. And this comes out to about 9. It's about 8.87, but you'll find that if you just round it up, we can plug it back in and see if that's exactly what it is, okay? So n equals 2. So that's going to be, so in theory, we think it's going to be from the n equals 9 to the n equals 1. That's what we think it is. But let's plug it back in and check. So I say, okay, 1 over wavelength. We're going to solve for wavelength. This time is equal to Rydberg's constant. 1 over, and then this time is 1 squared minus 1 over 9 squared. Okay, that just becomes 1 minus 1 over 81 times Rydberg's constant is equal to 1 over lambda. Okay, so let's see, 1 over 81, okay, times Rydberg's constant. Again, the Rydberg's constant, all other constants are going to be on your equation sheet, so and they're usually in the top left corner, okay? So, 1 minus 1 divided by 81. And then invert it. Okay, now don't forget to invert. A lot of people just forget to do that, and that just really screws up their answer. So here I get, 92.26 times 10 to the negative 8th meters, which is really just what, 92.26 nanometers, which is pretty much 92.3. Okay, so that's the trick. That's the trick that you want to know. So now we know for sure it's n equals 1 to n equals 9 to n equals 1. Just using this trick. Most of the time, the ending end shell, is only going to be n equals 1 or n equals 2. Honestly, I have never seen in my 7 semesters of TAing it end up being n equals 3. So really just use this trick. If it's between 0.75 and 1, just plug in n equals 1. Or if it's between 0.139 and 0.25, then put in n equals 2. And honestly, I could explain the trick, but it's really going to take a lot of time, so I'm not going to do it in this video. If you'd like to know, you're welcome to email me, and we can do it over a tutoring session. All right, number 9, last one. Astronomers have detected hydrogen atoms in interstellar space in the n equals 800 excited state. Suppose an atom in that excited state undergoes a transition from n equals 801 to n equals 800. How much energy does the atom lose as a result of this transition? Okay, so now this is where I want to use this equation here. So I'm going to say negative 2.18 times 10 to the negative 18th. Joules times 1 over n final squared minus 1 over n initial squared. Okay, and remember there are variations of the same equation. I'm just going to use this one because I'm actually used to using this one. So then we say negative 2.18 to the negative 18th times 800, the inverted 800. So the n final, what is n final? N final is going to be 800, and n initial is going to be 801. Right, because it started there going down, so we're emitting, and so we're losing energy. So 800 squared inverted minus 801 squared inverted. Sorry, it's taking me a little bit to punch this in. All right. And then times. All right, and then I ultimately get about negative 8.5 times 10 to the negative 27th, okay, joules. Now this negative makes sense because I'm losing energy, right? This is an emission. I'm going down. And so I would lose that much energy. Now, obviously, that's not a lot of energy to lose. So this is the amount of energy I've lost. Now, what is the wavelength of that radiation? Well, I know that the relationship between wavelength and energy is this equation. So then I would say, in this case, you don't need to put a negative here because it's an absolute value. We're just looking for the wavelength of the photon that left. So in fact, it actually does have to be positive. So I'll just put 8.5 times 10 to the negative 27th joules. Joules is equal to hc over lambda. And we're solving for lambda, so let's switch these guys. So lambda is equal to hc over, and in this case, 8.5 times 10 to the negative 27th. Now, Planck's constant is not something you have to memorize, but it is useful if you just know it off the top of your head. And if you do this correctly, you should get about 23.3, or I'll say 0.4 meters. Okay, now that's a pretty big wavelength, right? In fact, part C says, what kind of telescope would astronomers need to detect radiation of that wavelength? This is, if you look in the electromagnetic spectrum, anything above 1 meter is actually going to be in the radio region. Radio. So you're going to need a radio telescope to be able to see this guy. Okay. All right, so that finishes it for problem set 6, the Bohr model. I hope that was helpful and that you understood a little bit more about the Bohr model.